Hello everyone. In this video we're gonna solve some transient problem. It's basically charging or discharging a capacitor through a resistor, or charging or discharging through an inductor, so something like that. So if you just have a resistor network, if you just have a resistance in the circuit, and if you, let's say, if you turn the power on, the voltage across the resistor will be turned on, right, instantly, right? It doesn't take any time delay. But however, if you put some energy storage device like capacitor, inductor in the circuit, then the voltage across the capacitor or inductor does not rise instantly. It takes some time. It takes some delay time, and it depends on the time constant of the circuit. And this is called, that delay time is called transient time. So that's why we call circuit something like that as a transient circuit. So since the voltage across the capacitor or voltage across the inductor changes as a function of time, right, changes with time, so it will involve differential equations, right? And then we'll have to solve how voltage will change over time, something like that. So the differential equations we'll be dealing with will be only three types. Actually, we'll be dealing with only three types of differential equations when you solve the transient problems. So, and these are some current and voltage relationship across the capacitor and inductor. So this is the voltage across the capacitor, right? Q over C, and that, and then the current through the capacitor will be C dV over dt. Similarly, the voltage across the inductor, right? L is the inductance, is given by that, and the inverse is so the current will be then the integral of VL with respect to time. And so we'll be dealing with differential equations of this type, right? This type of differential equation most of the time. So you have first order, the first two equations are the first order differential equations, right? And if you have both the inductor and capacitor, then you will have to deal with some second order differential equations. And we know the standard solutions of this type of differential equations. So we'll just be using the solutions, these standard solutions, right, to solve our transient problem. All right, so let's get started. And the first problem is this. So you're given a given circuit like that. The capacitor is placed here and it is charged, right, like that. So it says at t0, it says the first question is at t is 0 to at t is equal to 0, right, in the beginning, this two-way switch, the switch is connected to 1, right, like this. So switch is connected to like that, right? So then it provides a charging path, right? This is the battery, and the voltage across the capacitor will increase, right, exponentially with time, and then that's what it is asking you to find. So it's asking you to find out what is the mathematical expression for the transient behavior of the voltage and current across the capacitor if the switch is turned on at t is equal to 0, right? So, and then you can simply use Kirchhoff's laws, nodal analysis, to find the voltage relationship and keep it in differential equation form and then solve it. That's the standard way. So I'm gonna use, so when this two-way switch is connected to position number 1, then it completes this circuit, right? Then it completes this circuit, and it has so let's say this is the reference node, and you have how many nodes? You have several nodes like this. This is one node, this is another node, and this is, so let's call this is V1, let's call this is V of C. This is because this node is at the voltage across the capacitor, right? And this is at 21 volts with respect to ground. So then we can first set up our differential equation. It will be a first order differential equation, and then write down the solutions. That's it. So I'm going to use a nodal analysis to set up the differential equation. So I say at V1, at this nodal point V1, so KC, let's apply KCL, Kirchhoff's current law. Says, let's call this is I1, I'm going to call it I2, and I'm going to call this IC, right? This is I of C, current through the capacitor. And I1 is equal to I2 plus IC. This has to be IC, right? So I1 is 21 volts minus V1 divided by 60K. Let's keep it in kilo ohms. And on the other side, I2, what is I2? I2 is the V1 minus 0, which is V1 divided by R2 is 30K, right? Plus, what is IC? So IC is right here. This current and this current must be same, but this current right here is V1 minus VC divided by 10K, right? And then you simplify it, and if you simplify it, so I'm just going to write down the result. So if you simplify it, so it has these two unknown variables, so you'll get something like that if you simplify it, right? Your coefficients might be different, 2.33. So after simplifying, you get something like that. Let's say this is equation number 1, right? So you need one more equations, and so at VC, this is at V1, you get one equation. At VC, which is this node, at this node, you can say V1 minus VC divided by 10K must be equal to, this current must be equal to same current IC, right? Is VC divided by, you can simply say I of C, right? This current is equal to IC, right? But V1 minus VC divided by 10K is, I of C is the capacitor current. So this is, you can directly, in terms of capacitance, dVC over dt, right? Because the current through the capacitor is C dV over dC over dt, right? That's right. So you can set up a differential equation here, right here. So first you have to eliminate the V1C here from here, right? So if you eliminate V1C, so V1 is 0.67 VC plus 2.33 divided by 10K, and minus VC over 10K is C dVC over dt. And you can clearly see this is a first order, so you can again simplify this, just simplify that, and after simplifying and you're putting the value of capacitance, because you are given the value of the capacitance at 0.2 microfarad. 0.2 micro means -6 farad, right? Putting all these values, simplify it, and you will end up with a simple differential equation of first order differential equation of this type, right? Okay, so this is a differential equation of type dx over dt plus alpha x is a, and it has a solution of this type. Its solution is the solution of this differential equation I showed you in the very beginning, right? Is solution of this type of differential equation, first order differential equation, is Vc as a function of time is a over L alpha. Remember, this is a, right? This is your a, this is your alpha, right? Plus then some k constant, unknown constant that needs to be determined with the initial condition, and e minus alpha t. So this is the solution. This is the solution of this type of differential equation. So let's put that. So V of C t is, what is A? A is 1165, alpha is 165, plus K E negative alpha is 165 T, right? So but we still don't know this unknown constant k, and that needs to be determined by the initial condition. And what is your initial condition? Initial condition is at t is equal to 0, right? Or you can say 0 minus or 0 plus. This is 0 minus is simply just before the switch is turned to 1, and 0 plus is right after, immediately after the switch is connected to 1, and that must be same. 0 minus and 0 plus must be same. And what is the voltage across the capacitor in the beginning? 0, right? Because this was not connected to any source, power source. So this VC is 0. So that's your initial condition. This is called initial condition to find the unknown constant k in that solutions, right? So this is now using that at t0 0, right? So 1165, and that is going to give you 7. This 1165 over 165 plus k e to the minus 0, right? T is 0, and e to the exponential power 0 is 1. So that means k is, so this is 7, k is negative 7. That's it. So that unknown constant k is 7. So just put it here, and then you get the general solution. So the voltage across the capacitor as a function of time is, this is 7. So 7, and the value of k is negative 7, right? And E165 T, right? And you can do, yeah, that's your equation. That's your final answer. So this is how the voltage across the capacitor changes as a function of time. That's your answer, right? So, and it has that's the first part of the question, right? And let's see what's the second part of the question. Yeah, it's for voltage and current. So once you have the voltage, then current is simply current across the capacitor as a function of time is just dVc over dt, right? C, the capacitance, and dV over dt. So capacitance is 0.2 microfarad, and then if you just take the derivative of that, right? So you're just going to get 7 times negative 165 E 165 T. So I of C, right, the current through the capacitor as a function of time is given by this. So whatever you have this, so it's 7 times 0.2, 6 times 165 to be. So you can convert into micro amp. So this is how the current through the capacitor changes as a function of time, right? Alright, now if you want to calculate the time constant of this system, this circuit, how would you calculate the time constant? So just taking voltage or current, so this is something like VC is some initial voltage or 1 minus the exponent t over time. If you just compare that, your tau, which is the time constant, is simply 1 over 165, right? And that has to be 6 milliseconds. So the time constant of this circuit is, you can say, 6 milliseconds, right? Okay, that's the first part of the question, just finding the voltage and current across, voltage across the capacitor and current through the capacitor as a function of time using the. Alright, now let's do the second part of this question. So it says, find the mathematical expression for the response of the voltage across the capacitor and current through the capacitor if the switch is then thrown to the position B at 9 milliseconds of the charging phase, right? So after 9 milliseconds, this switch is now thrown to connected to position 2. Now it will find a discharging path through this resistor, and it will start discharging, and it's acting. How does the voltage and current discharges over time? So first of all, we have to find the initial condition, right? So at t is 9 milliseconds, what is the voltage across the capacitor, right? So, and from our part A, we know the voltage across the capacitor was changes based on this 1 minus c. If you go back and see, t over 6 millisecond is the time constant, right? And now if you put time as 9 milliseconds, right? So that's the voltage on the capacitor at 9 milliseconds, right? If you put that and calculate 9 millisecond divided by 6 millisecond time constant. So the voltage across the capacitor at 9 millisecond, you'll find, is 5.44 volts at 9 milliseconds. So which we're going to need later. We're going to need this initial condition later. Now, once you connect that, right, so you'll have a circuit like this, right? You have a circuit like that. Once you connect to the position B, your circuit is like this, right? This is IC. Let's say this is I of R. This is a 10 kilo ohm. This is a capacitor. And let's say this voltage VC, that's what we're, and this is the reference. So we can say at VC, you apply KCL again, right? So VC plus I of R IC, current through the coil is equal to 0, but IC is C dV C over dt plus, and that's VC minus 0 is divided by 10 kilo ohm is 0. Capacitance is 0.2 micro, right? dVc over dt plus VC over 10 kilo ohm. And now you simplify this. You simplify that, and you'll get this differential equation, right? Something like this. So dVc over dt plus, if you simplify, 500 Vc is equal to 0. Now comparing with, so this is your coefficient A, this is your coefficient alpha, and we know the solution of this type of differential equation is VCT is A over alpha plus K, right? The solution is like this, but since there's no, the coefficient A is 0, right? The coefficient A is 0 here, so this is just Ke minus 500 T, right? Because alpha is 500. So that's how the voltage changes over time. But we still need to find this K, right? This unknown constant K, which you can find the value of K using the initial condition, because at T is equal to 0, we know the voltage is 5.44 volts. So that's what we're going to do. So at T is 0, you can say 0 minus, or immediately before and immediately after, the voltage across the capacitor was 5.44, which we already found, right? So put that. So 5.44 is K is 0, which is K. So that means your K is just 5.44 volt. And then your general equation is the voltage across the capacitor discharges over time like this. So 5.44 exponent negative 500 t, and the time constant is 1 over 500, right? Like this. And 1 over 500 is 2 milliseconds. So 2 milliseconds is the time constant in discharge phase, right? So the capacitor will discharge through the 10K resistor, right, with a time constant of 2 milliseconds, like that, right? And you can find the current, how current changes, how current decreases over time is just the C dVc over dt, and that's going to be 0.2 microfarad, right? And D, you just need to differentiate this with respect to time. So if you differentiate over with respect to time, you get 0.2, -6, 5.44, -500, and okay. So this is how current through the resistor gets discharges over time. So I of C T is so you can now just do 0.2 micro times 5.44 times 500. So this gets you a negative current. Negative current simply means the direction of the current flips. This is 2 milliseconds. So this is how current changes over time. So the negative simply means the direction of the current changes as it discharges, right? So this is a differential equation method, right? Or you can simply use, so this technique, you can simply use this. So I'm going to show you, since the discharging, in the discharging path, you have a simple capacitor and a resistor, right? If you have a simply a capacitor and a resistor, you can directly use this general formula. You can directly use R, I'm going to say R. So the VC over T is V final, right? This is one of the formula, plus this is the general formula for charging and discharging a capacitor. If you know the resistance, if you know the T over tau, right? And so the final voltage is 0 because it will discharge, right, to 0 volt eventually. So initial voltage we found at 9 milliseconds is 5.5. You can directly do that, and your tau is just RC, right, which gets you 2 milliseconds. So this is going to be a very straightforward formula. If you want to do that, that's fine, but it may not work if you have multiple resistors, right? You can directly use, this is the general formula we have. All right.